We will be covering medical image reconstruction basics by looking at two simple data models using the example of positron emission tomography. I'll explain three different data formats, sinograms as well as backprojected images, and touch briefly on list mode data. And then we'll look at two models, convolution, very important to understand in imaging science in general, but also applicable to the case of 2D PET imaging. And then we'll also look at the radon transform and how that applies to PET data. So a quick review of positron emission tomography. This is a medical imaging modality used to image the brain, the heart, the body. Typically, we use a radioactively labeled form of sugar, a glucose analog known as fluorodeoxyglucose, and that's depicted here. But of course, it can be any kind of radiotracer, any kind of compound of interest. And so here with fluorodeoxyglucose, this radioactive sugar is injected into the bloodstream. The fluorine-18 in this molecule will decay by positron emission. A positron is going to meet an electron. There are so many electrons around, and you get matter-antimatter annihilation using E equals mc squared. We find out that the conversion of the rest mass of the positron and the rest mass of the electron, when converted to energy, gives us two 511 keV photons. So in a PET scanner, what we have then is high density crystals, and these high density crystals detect the pairs of annihilation photons coming off from the uptake in the patient's body of this radio tracer compound. And there I'm just showing some example back-to-back photon pairs, these 511 keV high energy photons, and they're energetic enough to escape from the brain or the body and to be detected by the scanner with these high density crystals. Okay, so let's consider then a single slice through the patient's brain here. This is a typical representation of the distribution of fluorodeoxyglucose in a patient's brains. This is just an enlarged transverse section, and we're considering a radiotracer concentration, calling that F, as a function of position R. So R is just a vector accessing, for example, an XY position within that slice in the brain. This, of course, is inside the PET scanner. The patient is inside the PET scanner, and the PET scanner detects data. And we're going to be covering in this video how these sinograms are basically obtained, because we need to model how they are obtained in order to even start to know how to do what we call a reconstruction, where we're trying to get some kind of parameter vector that's going to represent that distribution of the radiotracer inside the patient's brain, for example. So what we're going to do then is just have a simple depiction of that scanner field of view with the ring of detectors. And then that allows us to begin to define the reconstruction problems. We've got this slice of the brain, this radiotracer distribution inside the field of view. And that's giving off back-to-back photon pairs, these high-energy photons escaping from the brain. There are other factors that go on there, but we'll just keep a simple model here of just back-to-back photon pairs being detected by the ring of detectors around the patient's brain. And each of those detections is along what's called a line of response, basically a pair of high-density crystals detecting the two high-energy photons. And in image reconstruction, what we're seeking to do is reconstruct an object, okay? Reconstruct the representation of that radiotracer distribution inside the patient's brain. So it could be F of some vector R, or actually putting it into components X and Y. We're after this continuous function F of X, Y. But of course, we can't expect to find a continuous function, because it's that involves almost an infinite amount of information. And instead, what we do is typically discretize that into a set of pixels or voxels, little tiny squares or cubes that represent small areas or small volumes inside the patient's brain. So for example, if this is an XY coordinate system, typically we might have, for example, 256 pixels in the X direction, 256 in the Y direction, and so we'd be finding 65 million values. In other words, what's the concentration in each and every one of those little pixel regions? And so this is a very deliberately crude representation just to really drive home the point that typically we are estimating values for the radio tracer concentration in these little tiny squares, and you can see those very clearly in that depiction, and it means we're approximating that continuous function by a summation of these simple pixel box functions, if you like. That's why I've called them B, like a little basis function, and then we're finding values theta that are just scale factors indicating the concentration present in each one of those pixels. But again, this video is more about modeling the data acquisition to understand that better in order to prepare ourselves for estimating theta, the vector, when we're trying to do a reconstruction. Okay, let's get on then with understanding the model of the data, and we'll do that by using a point source of activity. So I hope you can see it. There's a very small point source there of radioactivity. This is going to be a positron emitting point source, and we're going to understand now what happens in a PET scan in a very basic way. So here then is our radio tracer concentration, F of R, and we've just got this point source of activity. Over here, I'm just going to do a copy of this image just to show what's happening here with the emission of two high energy 511 keV photons, and I've got the ring of detectors around that field of view again. And so with a detection, you'll see here I've kind of depicted an annihilation. The positron's emitted, it meets an electron, we get annihilation, two photons, and we're going to assume that they are detected at detector D1, D2. And then what we're going to see is how to understand how we can represent that line of response of detection through the field of view. So what I'm going to do first of all is take that XY coordinate system and just rotate it by some azimuthal viewing angle phi. I'm doing that such that this y-axis is now parallel to that line, and then x gives us the perpendicular distance of that line from the center of the field of view of the scanner. After rotating that XY coordinate system, I'm going to relabel it S and L just to indicate that it's not XY, it's now a rotated coordinate system. And then we can very simply use phi and S to indicate what that line is. In other words, any given phi and any given value of S will be able to define this particular line. So that back-to-back photon pair has formed a line of response of detection, crystal D1, crystal D2, and then we've got a distance S and an angle phi. That allows us now to say that we've collected one count of measured data. And so what we do is we create a coordinate system here, S and phi, where S is that perpendicular distance from the center of the field of view, and phi is the angle of that S from the x-axis. So you can see in this particular back-to-back photon pair from this point source, what we've got then is a distance S that's equal to 41.5. So I go along S, 41.5, that's about here, and phi is an angle of 19.7 degrees in this particular case, and so I go from 0 up to an angle phi of 19.7, and I just simply put one count there. So I've just added one value. I hope you can see it. It's just located in that position in this grid. Effectively, this is a function m, a measured number of counts for position S and for angle phi. And so I've actually discretized that as well. It is in practice. These are called sinogram bins, and we've just put one count in that sinogram bin there. Another way of looking at the data is to say, well, okay, if we detected an event, two photons here and here, then we could just again create a new array in a computer memory and just draw a line to connect between those two detection positions, and if you like, back project, just draw a line through an image connecting those 2 points. And we'll call that a back projected image because we're going back along the line of projection where we detected that count. Another way of considering the data would be just to record it in list mode format, and that's what I'm showing here. I'm saying that, okay, I've got a count at two particular crystals, D1, D2, or in general, two detection positions, D1, D2. And it may have happened at some time t that hopefully we can measure. There may have been some photon energy, E1 for photon 1, photon energy E2 for the second photon, and maybe some time difference of arrival between the two photons that allows us to get into time of flight measurements in order to begin to localize along that line even better. For simplicity, in this video, I'll focus on the case where we don't use time of flight information, and in fact, we won't use energy information nor time. We're just going to go into static understanding of data acquisition and data modeling. Right, so let's move on for this point source and consider a second back-to-back photon pair. So here there's another annihilation that has occurred, and it has to be said that the photons will be given off isotropically, so all angles with equal probability. Here we're just considering a 2D cross-section. So here with the isotropic emissions, we've now got a second photon pair given off at this particular angle. And so again, we can calculate a perpendicular distance s from the origin and an angle phi. And then that allows us to plot, to bin another single integer count into our sinogram array or matrix discrete function here. And so you can see now this is an angle phi, 98.4 degrees, a distance s, 27.5. So that allows me to go s, 27.5, phi, 98.4, and I add one count there. Or in the back projected image, I could just again draw a line connecting those 2 points. And in the list mode data stream, I could record another event. And you'll notice that I'm just using the same labels here. So D1, D2 is just a generic representation of which position or which crystal detected photon 1, and D2, which crystal or position was the detection point for photon 2, and so on for the other attributes. Okay, so now I've got the example of having carried on to detect 6 back-to-back photon pairs, and so the most recent one of those 6 is shown here. So we've got some distance s and some angle phi, and now you can see that I've collected 6 counts in my sinogram, and my back-projected image now corresponds to an intersection of 6 points. Incidentally, here I'm putting in the brackets the sum of the counts in the sinogram, showing 6 means that I've got 6 counts there. Here the value is the maximum value, I think it is. Right, okay, moving on. Now if we have 234 events, the most recent one is shown here, distance s, angle phi, and you can see now why, in fact, this m of s and phi is called a sinogram, because a point source is now clearly tracing out this sinusoidal response on the sinogram. The back projected image is now looking much better. We can see very clearly where that single point source is. And we could carry on to even more events here. So I'm showing the case of over 5,000 events now, and you can see we've got this very clear sinogram, and the back projected image as well is shaping up quite nicely. But you should notice that there's a very clear blurring effect, actually. So in other words, this clear point source has become this rather blurred function due to all the intersections of those lines. So in other words, there are these long back projection tails. So we can begin to build up complexity in our understanding now. Imagine we've got a collection of 10 randomly positioned point sources inside our scanner field of view. And then here again, I'm just showing the most recent annihilation photon pair that's been detected. And this is the sinogram that we'd get after 52,000, more than 52,000 events. And you can see that each of those point sources has given rise to a very unique sine wave result on the sinogram. And the back projected image now is again showing these 10 point sources, but each one of them you can hopefully see is a blurred point spread function. I use that term quite loosely. Many people would call it a point spread function, some point response function. It's basically some function that we can see is different to the original sharp point that was in the true object. We've got some kind of distribution, some kind of spread function. So often called a PSF or point spread function. Okay, let's now begin to build up then the picture of convolution, which is a very useful concept in many fields of image processing. So we can see that here, one of these point sources has effectively been replaced by one of those point spread functions, one of those blurring functions. Now, typically in continuous mathematics, we would describe this as a delta function. So we've got this very extreme case of a point, an impulse, or a Dirac delta function in the very limiting case. And with convolution, all that's really happening, particularly clearly, this can be understood in the discrete case, which I'll be showing you later on in this video. These delta functions are simply replaced by the point spread function when you do a convolution. That is all that is happening. We'll look into that presently. So let's now look briefly, though, at the mathematics before I go into that a bit more in detail using the simple discrete case later on. But we can see that if the true distribution is some function f of r, described as follows, and you can in fact view this equation as simply convolving the function f with a delta function, which means you just get the same function f of r. But really what this is saying is that we can represent our distribution f of r as a set of amplitudes, a collection of amplitudes f for each of the positions r prime, and then we use those as scaling or weighting factors or amplitudes. Ideally, really, I guess we call them coefficients for these delta functions positioned at all the locations r prime in that function. We just sum it all up. I'll go into that more in detail later on. And then all that's happening in convolution is that that delta is getting replaced by the point spread function to arrive at the well-known convolution integral. Again, I'll go into that in more detail presently. And just to point out again that convolution is very important to understand in many fields, and this is a very useful way of getting introduced to the convolution integral. Right, let's get back to our data acquisition case. Now imagine our positron emitting distribution was this more general distribution as shown here. So I've got a kind of a square, a large point source, a couple of lines, and a rectangle source. Then our sinogram would look like this. And you should realize that this is again just a collection, a superposition of point responses in the sinogram domain. So in other words, this square is just a collection of point sources of a particular amplitude. This is another collection of just 4 point sources of a different amplitude. A line is just a collection of point sources of another amplitude, and so on. So this is just a collection of point sources, and therefore with a linear system, which is what we're assuming we have here, the sinogram here is just a superposition of those sinusoidal functions that we get each and every one of them for each and every point source that's making up that original object, if you like. Now, if we just carry on with that back projection method that I was showing, earlier on we might have thought, well, actually that looks quite good. Seems like we can actually localize the sources very well, so why go about reconstructing it? Well, we can see very clearly that back projected images are quite poor in quality, and they're certainly not quantitative. Take a look at this object here. We've got this low amplitude, low concentration of activity for the square source here, and we've got this much hotter, higher intensity, higher amplitude, large point source here. And you can see in the back projected image, the apparent contrast between those two is actually the other way around. It looks like the square is hotter and this large point source is not as high in value as the square. So you can see the back projected image is giving us very big problems due to all of those tails that emanate out from each of those point spread functions. And you can see a lot of those tails also in this image. Okay, so if we were to build up complexity still further, then we could get to a simple brain phantom image, a bit like the one, in fact it is the one that you saw earlier in this video. This is a brain web phantom meant to depict an FDG distribution inside a patient's brain. And you can see again that we get a back projected image if we back project the data, or a sinogram here if we've collected over 100,000 events. A more involved phantom is the big brain phantom. I'm showing that phantom in this top left corner here. And you can see that for over 2 million events, the sinogram looks like this, and the back projected image as shown there. So this is just showing that, in fact, any distribution inside the PET scanner field of view can be regarded as just a collection of point sources at different positions with different amplitudes. That's the overriding point that I'm trying to make here. And then also the other point I'm building up is the fact that a back projected image can just be modeled for 2D PET by the convolution integral, where we're just considering each of those point sources as merely being replaced by a point spread function in the back projected image. And again, I'll go into that in more detail mathematically in a moment. So there are the equations, and I'm about to unpack those now. So let's take a look at this convolution integral. And after this, we will, of course, revisit those sinograms and model those mathematically as well. That's going to be an important part for finishing this video. But for the moment, let's focus on that convolution integral. So what we have then, this is another example of point sources. Here I've just got another collection of point sources. And here is that familiar looking kind of back projected image that we've been seeing before. And what I'm going to show is how these images very clearly relate to that convolution integral. And I'm going to be doing that by using a simple discrete description before returning back to the continuous form. So let's say then we've got some radioactive concentration F at discrete positions K and L inside a 2D array. So I've got this K value along in this, if you like, this X direction, and this L value in the Y direction. Okay, these are just integer indices of, if you like, the pixels in this 2D array, in this 2D image. So that's the true distribution, just represented as a discrete function. And then what we're saying is we've got some point spread function, H, which could also be represented on a grid. Now here I'm now using X and Y. Please allow me to do that. I'm going to use here X and Y as just also integer discrete coordinates along this in this 2D image here. So we've got H, X and Y, and so that's this function that is this point spread function with those tails that we've been seeing earlier. And here I'm just going to say, well, what if the true object was just a point source? Then all we're saying is that the back projected image can be found, let me just back up, can be found by convolving that true object with the point spread function. So what is the convolution doing? Well, what it's saying is that you basically visit every single location inside this image, and you can see it's all zeros except for where that point source is. And for where that point source is, we just simply take that point spread function, h of x, y, and we position it at the same position k and l. So that's why we do x minus k, because that shifts to the left. And then y minus l, that shifts it down. So remember that point source was in the middle. We're just doing a shift left and a shift down by positions k and l to locate that point spread function there. And then that's going to give us the back projected image if this was all that was in the field of view. In other words, just a point source, okay, convolved with a point spread function, just gives you the point spread function at that position, scaled by, if you like, the amplitude f of the true object at that particular position. So f is the amplitude there. That is a scaling factor. We get that scaling factor by looking up position K and position L. That scale factor is applied to h of x and y. H of x and y is just shifted to position K and L. And that gives us the output of the convolution, which is this back projected image, G of x, y. So you can see, hopefully, how simple this is for the case of a point source, okay? Now the point is that any general object is going to be a superposition of point sources of different amplitudes. So all we need to do is just repeat this for every single position K and L inside this true object. Now here, because we've only got one point source, we only need to do this once and we've got the correct answer. But But in general, there could be point sources somewhere else inside this object, and they're going to have different amplitudes f depending on position k and position L. Therefore, we get a scaling factor, a coefficient f, depending on position k and L, and we use that to scale up the point spread function h of xy shifted to the position kl of the point object that we're considering. So that's why we simply have to do this summation by basically summing up all of the responses by visiting all of the locations k and l inside that true object. Okay, and that is all that is going on in convolution. So we can view this true object as some function f of xy, and then what we use is, if you like, indices of integration of summation k and l to just visit those xy positions. And then when we visit those kl positions inside here, we look up the value f. We use that value f as a scaling factor, a weighting factor for h of xy, shifted to position k and l of that point object, sum it all up for all of the point sources. And that's how, for example, if this is the collection of point sources, that's how we get this superposition of point spread functions in the output. Now here this is noise limited, and so it's not a pure convolution. If I'd simulated infinitely many events here, then that would be a very smoothly varying function, and you wouldn't see those discrete tails there. But you get the idea. It's just a simple substitution. A point object gets replaced by a point spread function. Okay, and this is what we call a linear shift invariant system. Really, we should call it shift equivariant. It's called shift invariant typically just means that wherever we are inside this true object, that the point spread function looks the same. Now, strictly here, there are going to be edge effects, and so this is shift variant, but the model of convolution is that the point spread function is exactly the same shape wherever you shift it to. It stays the same shape, or rather, wherever the point is inside the true object f, the point spread function in the output is the same shaped point spread function. It is merely shifted to the position of the point inside the true object. Okay, so with that very simple understanding of discrete convolution, we should be able to see immediately how that just follows through to the continuous case. In other words, these discrete summations are just replaced by the integral summation sign. We still are visiting positions inside the true function, visiting values in x and y in the domain of f. So we're gonna integrate over x prime and y prime. Those, if you like, are dummy variables of integration. We're just using them to scan around all of the positions inside f, and then we get the value f and use that as a scaling for the point spread function h of x shifted to position x prime and y prime that's inside that within the domain of the true object. And then once we've summed it all up, that gives us the overall output. And we could write that as a 3D version using vectors instead of component notation there, and so that's how we'd get this very simple form. But really, I hope I'll win you over various other videos, not in this one, to say that this form here, when written in matrix vector form, is a really elegant and very powerful way of describing convolution, and matrix vector will be incredibly useful throughout your understanding of image reconstruction. Okay, let's move on. Sorry, this is just to finish the model of convolution, just to now say, having described that integral, hopefully you can see how the true object, when convolved with a point spread function, gives this, and that is none other than that convolution integral. Okay, right, I just want to finish this video by looking at the sinograms, because notice we've done a lot of modeling now and understanding of the back-projected image as shown here for this collection of point sources, but I now want to finish by talking about the model of the sinogram here. And that's often modeled by the 2D radon transform, or really the X-ray transform to be more general, and that will allow generalization to 3D as well. Right, to go about describing the sinogram using an integral equation, we're just going to consider what happens if we wait and collect lots of events along a particular line of response. So I'm representing a particular line of response by this dashed line here, and you'll actually notice that, to a good approximation, this dashed line, imagine that as connecting two crystals inside a PET scanner. You can see along that line there are in fact 2 point sources. As we wait and collect counts along that particular line of response, what we'll arrive at is a value in the sinogram that is proportional to the sum of the activity along that line through the scanner field of view. Okay, so you've just got to imagine, lots and lots of back-to-back photon pairs coming off from all of these point sources, and then if we just fix on looking at one line, and remember one line corresponds to a single point in the sinogram, that single point in the sinogram corresponding to that single line, that point in the sinogram will end up accumulating a number of counts that is proportional to the sum of activity along that line through the field of view. So what we're going to do is model that as a line integral. Okay, so we can sketch again our xy coordinate system and describe our point source distribution as some function f of xy. And we can say that this sinogram, this number of counts m as a function of s and phi, is approximately, I'm saying approximately equal to because there's noise here. These are actually Poisson distributed data, but we'll model it by saying it's equal in a moment. But just to say it's approximately equal to a line integral through this function f of xy. So for this case here, if you'd allow me to imagine that's a value of phi equal to 0, remember the xy coordinate system, well here the angle phi is tiny, there's a very slight angle on that, but let's consider it as 0. And then we've got some distance s, 14.5 from the center of the field of view, and that lands us approximately there. Then what we're saying is that the number of counts m is approximately equal to the integral of f of xy along axis y. So here's f of xy. Then what we do is we look at the position x here, so that's here, and we're just going to integrate along the y direction, just going to sum that function. And so here, s actually matches x if we are considering phi is equal to 0. And we're just summing the function along that line. Okay, then what we could do is in fact consider all of the sinogram bins along there, so all the values of s, okay, so all of the different perpendicular distances. So I'm showing that here by considering this collection of parallel lines now as we consider all of the positions along there. Obviously I would need to fill in all the gaps there, but I'm just spacing them out for clarity here. And then we could consider all of those line integrals and therefore obtain the value m as a function of s, or indeed as a function of x, because here phi is effectively 0. The number of counts as a function of s is just given by this f of xy, where all we're doing is integrating along the y direction. We're taking line integrals vertically all the way. So that will model one row of the sinogram, a 1D parallel projection. It's called 1D because this is a 1D function here. We've got m as a function of distance s for a fixed angle phi. But what we can now do is actually model the whole of the 2D function simply by considering all of the different viewing angles phi. So what we do is just rotate that collection of parallel lines, just rotate them according to the azimuthal angle phi, and that will allow us to now populate all of the other rows, if you like, all of the vertical axis values of phi to populate the whole of the sinogram. So I'm going to try and illustrate that by showing these blue lines to show that these are line integrals. And then what you can see here is I'm just rotating that set of lines. Okay, let's do that again. Rotating that set of lines, and that allows me to scan that line where I'm just visiting, where I'm basically finding the values of ms phi, As I change phi, so I'm rotating that grid, that collection of parallel lines, and it allows me to fill up all the values in the sinogram. And so in general then, our sinogram m, s and phi is just simply given by a rotated coordinate system. I showed you that earlier in the video, f of s and l, a rotated system where we're just integrating along the direction L, perpendicular to S. Just like here, S of course was in this direction, and we're integrating in a perpendicular direction to that. And if you want to understand the connection between S, L, and SL and X and Y, then we can just use these simple trigonometric equations here, which I'll let you examine in your own time. In fact, it's just as a quick note, it's easier to write these in a matrix form, where we'd have an output vector x, y, that's like the vector r that I had earlier, and then we just have a matrix cos phi minus sin phi, cos phi, and then we'd have s and l as an input vector to that 2 by 2 matrix to get an output vector x, y. Then we can just do the transpose of that to get SL related to x, y, and that just gets us the transformation between the rotated and non-rotated coordinate system. What we've got now, crucially, are two models for PET data. One is a very simplified convolution model, valid for 2D PET, and the other is the radon transform or the X-ray transform model. And you'll notice that both of these express our outputs, either a back-projected image or a sinogram, as integral equations of what we're interested in, which is the function f. So the image reconstruction problem is saying, how do we find f when we are only given either g or m? And so that will be the topic for other videos. I'll finish though by showing a good demo of the acquisition process that we've been looking at. So let me just change to a simulation here now. So here is that brainweb phantom that you saw earlier. And what I'm going to do now is just show you an animation, a simulation live of what is going on there. So here I've got the true radioactive distribution. And what I've done is simulate a point of positron emission. Positron meets an electron, gives back-to-back photon pairs. And I'm showing the annihilation photons as the red line again. And I'm recording the emission site here. And I'm plotting the S and phi value for that line here. And I'm back projecting it here. So I'll just show you a few of these, and then I'll let it run a lot more quickly. So to understand these lines and the sinograms and the back projected image, I'll just refer you back to those earlier parts of the video where I described that in detail. But this simulation will now hopefully tie it all together as I just step it through a few more, and now it's going to pick up speed. And we can see that this true representation, the representation of the true radio tracer distribution inside this brain section here, is what's allowing us to simulate back-to-back photon pairs as in a PET scan. And you can see here that we're gradually accumulating more and more counts in our measured sinogram. And you can see this is Poisson distributed. It's collecting integer counts that are increasing over time here. So here we're now over 5,000 of them. And here we are back projecting the data. And that, of course, is our model G of R that we talked about. This is the model for M, S, and phi that we've talked about. And then over here, we're recording the sites of positron emission. So another way of looking at that might be considering that as the ultimate in time of flight data, because if you were to back project and if you knew with incredible precision and accuracy the difference in arrival time between the photons, then you could of course just immediately plot the point of emission of the photon pair back in some 2D image to do if you like, a kind of direct time of flight reconstruction. Okay, so I'll let this run a bit more so you can see what unfolds as we collect more and more events. But meanwhile, hope you enjoyed the video. Thank you very much for listening.